welcome everyone. Today we have the pleasure of hearing from Serkan Guercin. And he's the class of 1950 professor of mathematics and a deputy director of the Division of Computational Modeling and Data Analytics at Virginia Tech. He's also affiliated faculty in mechanical engineering. He's authored a book on interpolatory methods for model reduction, as well as several book chapters and hundreds of journal and conference papers in the areas of model reduction, dynamical systems, numerical analysis, and scientific compute. Also, he received his PhD from Rice University, working with Anastasios Antoulis, and we figured out recently that he was there doing his PhD while I was there doing my undergraduate.
Yes.
So I took a class from Antoulis, but I never met Serkan back then. So it's our pleasure today to hear about interpolation for L2 optimal approximation.
Thank you very much, Laura. Thank you for the introduction, and then thank you for the invitation. I come to Michigan quite a bit. My in-laws live in Jackson. I make this trip very often, but this is my first time at U of M. It has been a very, very nice day talking to everybody, learning about their research. It has been a pleasure. So as Laura pointed out, I'll talk about interpolatory methods for L2 optimal approximations. I'm in the math department. My PhD is in electrical engineering. I come from a control theory background, and that's going to happen throughout the talk. This H2 part is very control theoretic, and then we'll start to move to more like numerical analysis, approximation theory aspects in the L2 part. I am hoping that we'll go through these two parts. This is probably not going to happen, but there are some extensions to nonlinear dynamics. So this is a kind of a overview of what I've been doing and then what we are currently doing in my group. So there's like a bunch of collaborators who have appeared, somehow contributed part of these things. Some of them are former students, some of them colleagues, some of them are still collaborating. So there's probably I'm even missing some people. So the problem, this is the main problem we are going to try to tackle. So I'm going to emphasize the theoretical aspects more in this talk than the computational aspects. So in my research, I have a lot of computational aspects, a lot of applications. But in this talk, I want to give the basics ideas, this idea of a Hermite interpolation appearing across different domains. We have codes for most of these things. We have many applications, but I'm going to keep this talk. There are some numerical examples, but talk will be most on the theoretical aspect. So this is our starting point. So we have a function, we have a parameter to output mapping. For the time being, I'm going to call this H, because that's kind of my transfer function from my dynamical system community. So I have a function H, which maps a parameter domain to C, let's say. And then my goal is to approximate this H. And then when you want to approximate something, you want to measure what you want to minimize. And then you want to have a class of system. What is your approximation going to look like? My approximation will be a rational function of H. Okay, so my H hat will be a rational function of that parameter P. And I'm going to tell you why I am doing rational approximation. And I'm going to find that H hat to minimize this L2 distance. Okay, so some measure mu and then over the parameter P. Okay? So throughout the talk, I'm going to choose this P and mu appropriately to cover different aspects. Okay, so this is the general problem. So towards the end, we are going to have a general optimality conditions for this setting, but then we are going to specify if I choose P this way, if I choose my measure from an integral this way, what kind of conditions do I get? For simplicity, in most cases, I'm going to talk about scalar valued functions, but the theory is all vector valued functions. Indeed, most of my examples will be vector valued. And then also for most cases, I'm going to talk about univariate functions, but some of this theory is already extended to multivariate case, but it's too much, I have already too much slides. And then don't worry, I don't have 48 slides. It's up to like 35. The 48 happens that we don't need to get that. Okay. So why rational approximation? So I come from a model reduction community. And then this is my You must have seen this in a control seminar. I assume everybody's familiar with something like this. This is the basic linear case. U is my input, Y is my output, X is my state. So I have my linear dynamical system, my state equation up top here, and then my output equation. So I'm not interested in all of X. I am measuring sensing X at certain location. X could be, the C could be averaging, or maybe measurement at a sensor location, whatever. And I don't care about X per se. What I care about is mapping from U to Y, okay? So my systems usually come from semi-discretization of PDEs. So it's my state, input, output. And in most cases, I mean, this is even at this point, somebody might consider this small. My state dimension, this X, millions, maybe more, okay? So in this case, control, even the simulation for this linear case could be difficult, especially if we had to do the simulation over and over again for different control settings. So our goal is to represent this dynamics with a reduced order dynamics. So I want to start from this large scale dynamics, and I want to reduce my A, my E, my B, my C. I want to go to this reduced model. That's the main idea. This is the simplistic perspective of model reduction. I am going from linear to reduced linear. And then this X set is my reduced state, okay? So what I want to do is that when I do this model reduction, so now this is a much easier system to simulate, control, whatever you want to do with it. But for this to be useful, if I feed the same input that I was feeding to my original model, when I feed the same input, it goes through my differential equation, my system. The output Y hat should be a good approximation to Y. Otherwise, there's no point, okay? So that's the main goal of model reduction. Come up with a reduced model, but make sure that your reduced output, reduced quantity of interest, is a good approximation to the full output for a wide variety of choices of inputs. Are we good so far? And then no need to wait until the end to ask questions. Really, just please no. And then classical way to do this, I'm not going to tell you, we are not going to do it this way, but usually this is what happens. You do basic projection-based model reduction. You find a basis V hat such that your large state space N approximately lives in this R-dimensional subspace. And then you plug into the differential equation, and then you project. So this becomes your reduced E, reduced A, reduced C, reduced B. So you choose this basis, V and W. Once you choose them, you hit your large quantities with them, and you reduce them. I'm not going to spend too much time how to get that V, how to get that W, but that's what all model reduction community tries to figure out. What is a good V? What is a good W? Such that reduced model is a good one. This is the classical projection-based model reduction. Okay? So where the rational function comes in, why am I asking my reduced model H hat to be a rational function? For my dynamical system, that looks like this. Obviously, we know this from our first ODE class. Output Y can be written as a convolution integral. Okay? So there's a convolution kernel. We call it impulse response. I take this convolution. So if you give me the input U, if I know this impulse response, I can convolve them, and I get my output. Okay? So convolution becomes multiplication in the frequency domain. So I'm going to take the Fourier transform. In this case, I'm going to take the Laplace transform. I'm going to convert this input-output map to mapping in the frequency domain. So this convolution becomes multiplication in the frequency domain. So take U of omega as the Fourier transformation of U, Y of omega as the Fourier transformation of Y. And then what is this function H? This is the function H we call the transfer function. Okay? So the transfer function H maps to input to the output in the frequency domain through multiplication. Okay? And then for this dynamical system, I can explicitly write it down. This is the transfer function. If I know this quantity, I know everything about this model. Okay? And then this is nothing but, here's the, you look at this middle, there is always showing up there. This is nothing but a degree n rational function in S. Okay? If my internal state is n-dimensional, H of S is a degree n rational function. So I can write it as a ratio of two polynomials, or this is what I'm going to use mostly. I can write it in so-called pole residue expansions. So these are the poles of this rational function, so the roots of P. And then these are the residues of the rational function. Okay. Same thing happens for my reduced model. Since I want my reduced model to look like the same, I am going to have a reduced transfer function, which will be also a rational function. The difference between these two, one of them is a degree n rational function, the other one is degree r rational function. At this point, you can completely forget about dynamical systems model reduction. You can just look at it from a pure approximation theory perspective. Given a rational function of degree n, how do I find a good rational approximation of degree r? You can just start from there. But for me, I have my dynamical system in mind. That's why I want my reduced model to have a rational function, because then I can write the ODE for the reduced model, then I can simulate. Any questions? So then these are going to be my parameters of my reduced model. These are the reduced poles, and these are the reduced residues. So these two are parameters, completely determines my reduced model. Okay? So, and then I'm going to do this via interpolation. I'm going to call this degree r rational function a Hermite interpolant to H at this interpolation point sigma 1 to sigma r if H hat interpolate H at sigma I, but also H hat prime interpolates H prime at sigma I. That's what we call a Hermite interpolant. Okay? So why 2r? Because I have 2r degrees of freedom, I can indeed satisfy 2r interpolation constraints. Okay? So that's what we are going to go after. Our approximate H hat will be a rational approximant, and then we are going to enforce that H hat is a Hermite interpolant to H at some spatial point sigma. Any questions so far? Yes.
Sorry, if you use elements, I mean, say interpolant, what we learn is the numerical methods class is that the OPT coincides with the correct function at those points, but it tends to show, you know, say, the large oscillations in between, right? If there are many points, you don't mind that?
So are the people on Zoom able to hear the question? So the question was that if there's a Hermite interpolant, so sometimes it could happen that maybe there's a growth in between. So in this case, that doesn't happen in this case. What we are going to show is that Hermite interpolation is what you have to do if you want to have optimality in the measure I'm going to focus on. So then we need to choose a measure. Okay, so now I chose the structure of my approximant. And then this is the key, that if I can make H hat close to H, then I can guarantee that Y hat will be close to Y for any permissible input U. Okay? So what is the measure I'm going to choose? I'm going to choose the H2 measure. H2 is a Hilbert space of transfer function with stable dynamical system. Pretty much, you want this integral to be finite, pretty much. So in our case, even though there are extensions, I am going to assume that my original system is asymptotically stable. There are extensions to this, so meaning that I'm going to assume that the poles of the original system live in the left half plane. Okay? I have an asymptotically stable dynamical system. This H2 measure is fine. So this is a Hilbert space, and then transfer functions of dynamical systems, stable dynamical system, are in the space. And what is the inner product? If I have two transfer functions, this is the H2 inner product, and then this is the corresponding H2 norm of that underlying dynamical system of order transfer. It's nothing but the energy on the imaginary axis. That's what it is. Okay. So how does this relate to this L2 measure I was talking about? It is. I mean, it's just you choose the regular Lebesgue measure on IR, and then your parameter domain is the imaginary axis. Then what I said is then the P is equal to S. What I define as the L2 measure for this choice becomes the H2 norm of a dynamical system. So we are in a subcategory of this more general L2 setting that I've been talking about. So this is what's going to come up. This is, at the end of this talk, I want two takeaways. One of is the Hermite interpolation. The other one is idea of mirror images. These things are going to keep coming up when you want to do L2 optimality. So what is this? So assume that I have a two dynamical system. Take this H is the original one, degree n rational function. This is my reduced model, reduced transfer function with pole lambda. one can easily show that this integral, this inner product, can be written as a weighted sum. Okay? So what is this sum? What I do, if I'm taking inner product of these two functions, I take the first function and I evaluate it at the mirror images of the poles of the second function. Okay? And then I weigh by the residues, I add them up, and this is just comes from you just apply the residue theorem, it's just basic application of the complex analysis, and then you end up with a beautiful result. Okay? And then these things start popping up. Mirror image of the poles. So again, minus lambda is in the left half plane, minus lambda is in the right half plane. Then of course, then you can do the H2 energy, and then again, you can even compute the H norm using the same evaluation. And then a nice result out of this, if I have two transfer function, I can plug this formula in here, and then I have an explicit formula of the H2 distance between H and H hat, which only pretty much depends on the parameters of the reduced model that you want to find. Okay? Again, evaluate the full transfer function at minus lambda, and then do this. I mean, this doesn't matter, right? If you are doing optimization, this is constant. This is the norm of the full model. So you want to kind of minimize that tail. Okay? So this mirror image is going to keep coming up over and over again. Any questions? Okay. So then where's the interpolation? Because I said, okay, mirror image, Hermite interpolation. So where does the interpolation come here? It's about to show up. And this is the first problem we are going to look at. Somebody gave me a full order model H. I want to find a degree R rational function that minimizes the H2 distance. So what is the best degree R rational function that minimizes the H2 distance? Okay? And then somebody might ask, why do I want to use this H2 measure? I mean, this is nice. It's come from a Hilbert space. Does it give me anything? It gives us this beautiful upper bound. So the L infinity distance in time domain, so the maximum mismatch between the full Y and the reduced Y in the time domain is bounded by this frequency distance between H and H hat and the L2 norm of the energy. So if I can make this small, I am guaranteeing that my outputs are going to be close for any input, L2 input that you have chosen. Okay? This is why we try to minimize this H2 distance between this transfer function. Indeed, for single input, multiple output, or multiple output, single input systems, this H2 norm is an induced norm of the underlying convolution operator. Not for multi-input, multi-output case, upper bound always holds, but for single input, multiple output, multiple input, single output, or single input, single output, H2 norm is the L infinity induced norm of the underlying convolution operator. So there's a direct link for model reduction. Okay? Of course, this is a non-convex problem. I am not an expert in optimization. For me, finding a global minimum is that hard. Maybe Laura can help me to find the global minimum. So I'm going to go after the local stationary points. That's what I'm going to go after. And it's going to be I'm going to try to formalize my reduced model in terms of the poles, lambda, and the residues. But where is the interpolation? I started my talk with the interpolation. Where the heck is the interpolation? Interpolation comes in this fundamental theorem. Okay? Given a full order dynamical system, assume that this is the best you could do. Assume that H hat is the best degree R rational function that minimizes the H2 distance. Then, here are the necessary conditions. H hat should interpolate H at minus lambda. These lambdas are not the poles of the full model. These are the poles of the reduced model. Okay? And then that's not enough. H hat prime should interpolate H prime at minus lambda. So if you want to have an H2 optimal reduced model, you'd better do Hermite interpolation. And then you need to pick your interpolation points as the mirror images of your reduced model. Okay? So that's why I always loved interpolation, but here it also comes as a necessity from a model reduction perspective. Okay? So of course, There's a chicken and egg problem here. Use optimal interpolation points. So let me go back here briefly. I am not giving you the computational things here, but if you give me the interpolation points, constructing a chat that does it is simple. If somebody hands me the interpolation points, I can easily construct a chat that does the Hermite interpolation. But here, I have a chicken and egg problem. The reduced model is interpolating at the mirror images of its own poles. I don't have this ahead of time. Okay, so the interpolation points depend on the reduced model I want to compute. This is a nonlinear optimization problem. You cannot do this in one step. You will have to iterate to do this. Okay, so that's the tricky part, that they are not non a priori. There are some work that gives the interpolatory conditions from a Lyapunov equation perspective. In this 2008 paper, we showed that you do interpolation or this, they are equivalent. Yes, please.
Is this sufficient also?
No, I'm going to touch on that briefly. This is necessary conditions. It is all I'm going after are the stationary points, and I'm going to have an algorithm that only converges to local minima. That's all I can guarantee. We have a method that we have a trust region version of it, but I don't have a method that can go to global minimum. I have no idea how to do that.
And then my other question is there any intuition of why the mirror images are important for this?
So it's all in here. It's all in this, like the inner product already carries the mirror. Maybe they do the intuition I can give you is the following. The poles are in the left half plane. So I am evaluating on the imaginary axis. Okay, like it is not exactly here, but in the H-infinity approximation, like you want the imaginary axis to be kind of you want a uniform behavior on the imaginary axis, okay? So then you want to balance where the poles are with where the zeros are. That's where the intuition I can give from the mirror image. Is that making sense? Yes.
In what areas of this theory are you assuming real quantities for things? It looks like in some of your coefficients for your state spaces, you're assuming real quantities.
Good, very good.
Because it seems like that might affect the mirror image result.
Okay, so very good. So the question was, where am I assuming realness? What I'm assuming realness are the state space quantities, but the poles and the residues are going to be complex. So poles will be complex, residuals will be complex values.
So if you assumed complex values for your state space parameters, you still get the same mirror.
If you assume complexity here, so then there is a little bit more complexity. Then you end up with conditions depending on the single input, multi output. You will get things like interpolate at the mirror images of the poles. But the conditions are really the same. It's either the minus lambda or minus lambda bar. So I can get it.
That's what I was getting at. So it's a minus lambda bar condition.
Yeah, but since I am assuming that I am going to have a real state space, they appear in conjugate pairs, I can write minus lambda or minus lambda bar. Did that make sense?
It does. Thank you.
Okay. Other questions? And then the derivation, one can think of the derivation in two ways. This was my error, which is a function of these phi's and the lambdas. Of course, this is tricky. I am saying set the gradient to 0, but this is really hand waving in a sense. This is a real valued function. I am differentiating between the complex variables, so you have to be careful. You need to do some other calculus here, but you can think of it. I mean, you can assume you don't even need to assume that, but like you can think of it. Take the cost function, differentiate with respect to residues, and then you obtain, this is your gradient. You set that to 0, you get the first order condition. You take this cost function, differentiate with respect to the pole, you get the Hermite condition. That's one way to see this. Much more, a better, more formal interpretation. You can look at it from a manifold of rational functions of degree R, and then you look at the tangent space of this. The tangent space is spanned by 1 over s minus lambda and 1 over s minus lambda square. You just enforce the orthogonality to the tangent space. This one gives you h minus lambda condition. Second one gives you h prime of minus lambda condition. There are many other ways to think about these things. That's where the mirror image in this is coming from. Again, as I said, poles and residues, interpolation poles are not known a priori, so we iterate, and that was what we developed in the 2008 paper. What we do, we get an intermediate Hermite interpolant, we examine it, we correct the interpolation point, we repeat the process until we reach the first order conditions. That's what we call iterative rational Krylov algorithm, IRCA for abbreviation. So we have a way to enforce these things numerically. And then here's a very simple example. This is an example, like this is a really old example from 2012. We were involved with some energy efficient building design project. At Virginia Tech, our job was to simulate indoor air velocity, temperature, and moisture in some kind of conference room. So what are the inputs for this dynamical system? We have inlets, the temperature were those were the inputs, outputs. We measure the temperature over here, and we measure the vapor mass fraction in some way. Details are not important. You have a PD, you linearized, you discretize. We have a dynamical system of order 200,000. Okay? So it's a linear dynamical system, order 200,000, 4 inputs, 2 outputs. So we did apply this H2 optimal reduction theory. We applied IRCA. We reduced to 30. And then this is some comparison of the outputs. I mean, we have many inputs, many outputs. I'm just showing first input to both outputs. Like, this is the behavior of the original system, reduced system, does a very good job matching the moisture and the temperature. I mean, I can show you the H2 numbers too. I mean, since you can guarantee this upper bound, this is a predictive, you can do prediction here, right? Because in this setting, we can do that. So this is just one example. We have many other examples. We have this theory. We can do this just from data and stuff like this. But I want to continue. And then, Laura, back to your question. When does it become global optimal? So if I fix the poles, if somebody says that I want my reduced model to have these fixed poles, then it becomes a quadratic function. And then this condition then becomes necessary and sufficient. And it goes back to Geyer. He did this on the unit disk. When you go to unit disk, think of this mirror imaging as a reflection. For continuous dynamical system, you are reflecting across the imaginary axis. For discrete dynamical system, you are reflecting across the unit circle. Okay? The theory beautifully extends. The first thing we said, what else we could do with this? Okay? In our case, we were interested in, so this H2 norm that I defined gives the same weight to all the frequencies. I am treating all the frequencies the same. But in some applications, you might want to put a different weight to a different frequency. Okay? This comes in control reduction. You look at the closed-loop transfer function. This closed-loop transfer function gives you how you should weight your error. Okay? So that leads to the idea of a weighted H2 measure. Okay? So I have a weight function. Now my new L2 measure is that I am not looking at the H2 norm of H2 norm of H anymore. I am multiplying H with a weight function, and then that weight function tells me which frequencies are more important than the other. So in this case, the problem is find H hat that minimizes the weighted H2 distance. No longer the regular H2 distance, but the weighted H2 distance. Okay? This is very, really common problem. Usually this is the closed-loop transfer function in the control reduction setting. And we made the assumption that our weight function is also a rational function. So we are assuming that our weight is also a rational function, in this case, degree NW. Okay. Things are going to start getting ugly with these formulas. I apologize. These things are going to keep popping up. This frac H. I'm going to keep defining this frac H. Frac H is the modified output. I have the H is the original function. Frac H is the modified function. Okay? So given the original transfer function, given the weight, I define this modified function frac H. Okay? This is really a bounded linear transformation from weighted H2 space to H2 space. You can write that down. And then what we show is that given the full model, given the weight, if this H hat is the best degree R rational approximation in the weighted H2 norm, then you still need to do Hermite interpolation at the mirror images. But what you are interpolating now is no longer H, you are interpolating this modified mapping. you are still interpolating at the mirror image of the reduced poles. Still the same thing. But now the function to be Hermite interpolated is this crazy looking function. Okay? But again, the critical thing is Hermite interpolation at the mirror images is still the necessary condition for the H2 optimality in this setting. Does that make sense? So unlike to do this, like for the previous case, we had this ERK algorithm, we get these conditions exactly. Here, we don't have a projection-based algorithms to get these conditions exactly. To do this, our projection-based algorithms only get them approximately, but if you can do maybe optimization, just optimize based on these quantities, then you might be able to get these things exactly. But the conditions are the same. Okay. Are we good so far? Okay, so now we're going to move to this L2 setting, the initial thing. So now I'm going to maybe step slightly away from dynamical system. It's still going to be the dynamical system. I'm going to go to, okay, let's revisit the L2 setting. What else we can do this? Because I was in the L2 setting, I choose P to be the imaginary axis, I choose the Lebesgue measure, I got the H2 norm. What else can I recover from this? So, and then so I have a now mapping Y, which maps the parameter to something, again, scalar C. So here I'm looking at two problems. Here the left, well, okay, your left for you too. The left-hand side, think of it as a weak form of a stationary PDE. Okay? And the right-hand side is my dynamical system in the time domain. I do some discretization to my PDE, and then I have this thing. Okay, so I have a parametric stationary PDE. Okay, I am abusing notation here, but in the control community, use the input, in the PDE community, use the solution. So here's the solution. Okay, so this is my stationary parametric discretized symmetric PDE. Okay, and then I am doing the observation. Dynamical system analogy of this, I took the Laplace transform. ODE part turned into this, and then my output turned into this. Okay, these are the same problem. Left-hand side and right-hand side, I can treat them the same. Okay, they can be both written in this kind of general way. Blue corresponds to this, and then the red corresponds to output. So in this general form, P is my parameter. So in the PDE setting, theta is the parameter. In the dynamical system setting, frequency is my parameter. Okay, so I have some of the terms. So in this case, in this case, I have QA is equal to 2. So I get A1 and A2. What are these coefficients? Coefficients of A1, so in this case, lambda 1 is equal to 1. Let me write it in it here. In this, on this, as alpha 1 is equal to 1, alpha 2 is equal to P. That gives me this. And then on this side, on the ODE side, I have alpha 1 is equal to S, alpha 2 is equal to -1. Same thing. Okay, that's it. And then in the PDE side, I am choosing the theta to be the parameter. In the ODE side, I am choosing frequency to be my parameter. Okay, and then in this case, my right-hand side doesn't have any summation terms. So in both cases, this sums Q sub B is equal to 1, Q sub C is equal to 1. This is what we call affine separable form. And this is very common in the parametric problems I deal with, that I can write this dynamic part as a sum of different functions. Okay, so it could be, this is a very simple case, but this could also be A1 plus some other function, in this case like theta A2, but maybe I have theta squared A3. Just affine parametrically separable. This is very common in model reduction. So now my goal is I have a parametric mapping from P to whatever that parameter, whatever the output is. And I want my reduced model to have this structure. I don't know what is the structure of the original model. I don't have access to the original model. I have access to the Y, which could be evaluation, which could be sample. I don't know what it is. But since many models I deal with in practice have this structure, like my dynamical systems, I'm going to enforce my reduced model to look that way. Okay, I don't know why it doesn't have to look that way. But my reduced model, I'm going to enforce the structure on my reduced model. Okay, so in this case, my reduced quantities are going to look like this: reduce A, reduce B, reduce C. So what I'm going to assume is that I know this parameterization, I know what these coefficients should be, but I don't know what these matrices are. So I'm going to solve for A hat I, B hat I, C hat I. If you are familiar with the operator inference in the model reduction community, there is some connection to that. But operator inference results in linear least squares problem. Since I am going from input to output map, we are going to have a nonlinear problem here too. But you can think of it, you are learning the operators of the reduced model. You can think of it that way. Yes?
I want to make sure I understand. So you're saying that alpha hat, beta hat, and gamma hat are specified.
I know, I am assuming I can choose them and I have an idea. For example, if I am working with dynamical system, I'm going to choose alpha 1 to be S, alpha 2 to be 1. Okay? If somebody said that I have a parametric PDE, maybe they have an idea of, but you can choose some. You can choose to be sine theta. I'm assuming that somebody has a good idea how to choose those coefficients, but they don't know what the corresponding matrices are. Does that make sense? Other questions? Now, this is our problem. Problem get more complicated. I want to, again, this L2 distance between the full output and the reduced output, whatever measure you have chosen, with the constraint that my reduced model will look like this. So my optimization parameter domain grows drastically here. Okay, I have many more parameters, and this optimization problem scares me. I was telling Laura earlier that this is like, it's very difficult for me to see a lot of parameters for me, but this is a very common problem in the model reduction community. Solve for this, and that's your reduced model. For these things to make sense, there are various technical assumptions, what these coefficients should be, what should be the P mu, and then fortunately, as we have shown in some papers recently, that these assumptions that are necessary for this problem to make sense, they trivially hold in many cases. And then this is the general L2 optimality conditions. I call them integral L2 optimality conditions. It looks very complicated. The main message is this is the quantities you evaluate from the full model. All you need is data. You don't need this state space. Those quantities needs to be matched from the reduced model. Okay? And then, indeed, this is much more general than H2. This automatically covers H2. If I go to these integrals, if I choose this P to be the imaginary axis, Lebesgue measure, choose the alphas accordingly, they automatically give me the Hermite interpolation conditions that I had before. This becomes the interpolation condition of the derivative. These two, for the single applicate, they give you the same thing. They become the regular interpolation condition. This is a much general condition than H2. Okay? And then really, you don't need state space. You can evaluate those integrals from data. Okay? And then in this paper, that's what we did. In this first paper by Petar Milinich, my former postdoc, he really drew this. He really was the main driver behind this work. So indeed, he was able to compute gradients explicitly with respect to all these parameters, and we just ran gradient-based optimization to get those optimality conditions. Okay? But this is really like, I am not assuming that this doesn't require rationality. When I do rational approximation, I got some more interesting things. So then what we are going to do now in the rest 10 minutes or so, we are going to take these conditions and then we are going to start enforcing structure on the reduced model. We are going to enforce some rationality structure on the reduced model, and then we are going to enforce certain structure for the measure and the parameter domain to show that Hermite interpolation keeps showing up over and over and over again. So here is the very common setting that I work a lot in. I collaborate a lot with mechanical engineering colleagues from structural dynamics, and then we can measure transfer function samples at frequencies. Okay? We shake structures, and we can hit them with a hammer, then you have some input-output data, you do some transformations, and you get the frequency response data. It's a very common problem that it appears in structural dynamics in my line of work. So the problem is that I don't have state space model. I have the samples of my transfer function on the imaginary axis. Okay? Then what I want to do, I want to find a rational function, my reduced transfer function, to minimize the least squares error in my data. Okay? Rational least squares approximation problem. And then this is indeed the L2 optimal problem. If I choose this special measure, like some of the Dirac measures at the frequencies, and then again, my parameter set becomes the frequencies that I have to sample. So this discrete rational least squares problem is really a subset of this more general L2 optimization problem. Okay? So then what we did, we took these conditions, we plugged in this measure, this structure, and then what comes out of it? Yet again, Hermite interpolation at the mirror images. Okay? So assume that, so this is my reduced transfer function rational. Assume that this transfer function minimizes this discrete least squares error. Okay? Then it turns out that, bless you, it turns out that this reduced transfer function should enforce Hermite interpolation once again at the mirror images. What has changed? The function we have to interpolate. Okay? So this is the this modified function. I am no longer interpolating h. I have a function that depends on h. I have the corresponding function coming from the reduced model. They gotta interpolate each other. Again, Hermite interpolation at the mirror images. That's what you require for L2 optimality, in this case, discrete least squares problem. Okay? You can put weights here and stuff I am not putting here. And here's an example. The model, we have some colleagues at Onera. They have this flexible aircraft model. We got the model and data from them. So pretty much they tried to model the influence of wind gust on a flexible aircraft. And what they gave us, there's a single input, which is the gust disturbance. And then this problem is a lot of outputs. I have so many measurements. I get 46 acceleration and moments at different locations on the wing. So that is the input output. I have a single input, 92 output transfer function. And then we have 420 frequency samples. And here are the samples. This is of course, this is a vector. So we are plotting the norm of the transfer function at every frequency. It's like a body plot, vectorized. So that's the data. Okay? So you want to fit a rational function to this data. Indeed, you can think of it as the 842 samples because you add the conjugates as your question to this data as well. So we have an algorithm. We pretty much did we just really throw an optimization to this conditions. And then, so this is the error. We have a reduced model. So the learner is an approach very common in the data-driven modeling community, in the dynamical system community. That's the baseline. And then with our L2 conditions and Hermite interpolation, we were able to reduce the error by more than order of 1. Okay? So again, whether you have a data-driven problem, least squares problem, or the H2 problem, continuous measure, it didn't matter. Hermite interpolation is a necessary condition, and then you can get very accurate approximations to do that. Okay? Questions? Okay. And then I also, in this L2 case, I also mentioned the stationary parametric problem. Here's my problem. Some stationary problem parameterized this way. And then I want to have a reduced model that looks like it, but it is reduced. And I want this reduced output to approximate this output. It could be a stationary parametric problem, but really, if you solve for this, output y is still a rational function in P. Okay? So you might think, oh, this is not a dynamical system. I don't need rational functions. It appears naturally. Okay? So for my reduced model, I can have a rational function. In this case, my parameter is not frequency S. It's to whatever the parameter I have here. Okay? Then this is even uglier than before. you define these modified frag functions. Again, frag y, frag modified outputs. So assume that you approximate this stationary PDE with this one. For this to be optimal, you're going to do Hermit interpolation. Again, Hermit interpolation becomes a necessary condition for optimality, even in the stationary case. Okay.
This is not the mirror image.
Very good, very good. So why isn't this the mirror image? The thing is that because in this case, the poles are outside my parameter domain. The mirroring is coming from there indeed in this case. Okay. So you can think of it in the dynamical system case, poles were here, interpolation points were there. So these are my interpolation points. They are indeed outside the region of interest. So that perspective is still there. And then use the example, we took this Poisson equation, coefficient is parametrically varying. So I mean, we chose some parametrization. Here's our parameter interest. I think Petar did the discretization. It's a small model in this Poisson equation. Order 1000 was enough. Single input, single output. We did a gradient-based optimization to solve this L2 problem. It converged the Hermit conditions. We have an order 2. And then, Laura, these are the poles. As you can see, poles are outside like that mirroring is automatically there. You can think of it that way. Okay? So those are the, and then our reduced models were, so for those who does model reduction, there's POD, there is greedy POD, stuff like this that one can do. When you apply this more proper L2 based optimization, you get much more accurate L2 approximates because you are satisfying the optimal condition to start with. And then like these are the functions. So this is not the output of the Poisson equation. So this is this modified output. And this is my reduced modified output. I mean, they're on top of each other. If you look at the error, I have Hermit interpolation at those 2 points. Just beautifully, Hermit interpolation shows up in this setting as well. Okay. Any questions? We have code, all these codes, everything is available in these papers. Petar has been very good, so you can download the code, play with these things if you want. Yes.
The plot you just showed.
Yes.
I think this comes back to like how sensitive are these interpolants to being off the points. I think this is the question that was asked earlier. So if I understand correctly, the optimal H2, if we go back to the original result, these are necessary conditions to satisfy that, but there are multiple solutions that satisfy the equation, so they're not necessary. So that means that there can be interpolates that are, they interpolate the data, but off the data, they can be very poor potentially, right? Because they're not optimal in the H2. And like in this plot, like the parameter range is -15 to 15.
The parameter ranges, and I'm plotting in the more general case, the parameter range is 0.1 to 10.
Okay.
I am plotting on a larger space here.
Oh, okay.
And then the interpolation points are outside the parameter range. Because I am interpolating, in this case, I'm interpolating at the pole. They are outside the range indeed. So
Yeah, so is there, I guess getting back to the crux of the question, is there anything that you need to do to regularize? Like you're going to do an iteration, you're going to finally satisfy these necessary conditions, but out of all these necessary conditions, some are potentially poor, some are the.
Very good, very good.
It's going to be, I guess you already said this already, you're going to be except local, like you're going to satisfy the.
Yes, very good, very good. So there are a bunch of reduced models that satisfies this, right? So what happens to this H2 error that I have here? At the optimal, in the L2 stuff, what happens at the optimal, if you have you end up with H2 norm of the full model minus H2 norm of the reduced model. And you want to find the one that satisfies the conditions but has the largest H2 norm. I don't know how to enforce this. Okay, so we have a version, this ERCA that I mentioned here. It is really just a fixed point iteration. At least we were able to prove that when we converge, it is at least a local minima because we showed that other saddle points are repellent. We cannot converge to those. So we have a gradient that trust region based methods. At least we can guarantee always kind of a monotonic decrease. I hardly advertise that because the simple ERCA iteration was really enough for most of the case. So it requires, of course, as mode optimization, probably you need to have some good initialization, right? So the way to think about this, so original poles are over here. Interpolation points are over here. Okay, and interpolation points are the mirror. Well, that we should be a little bit more poles than interpolation points. So then, if I mirror them, they are ending up here, right? So that reduced poles should not definitely they are not gonna exactly approximate the full poles, but probably they're gonna be in a somehow in a kind of domain. So if you have an idea where your important poles are, you just initiate your algorithm there. So somehow algorithm finds its way to find a good local optimal, but I can never guarantee global. But really, algorithm somehow coming from the underlying issue structure, I think, has been pretty robust to this. And biggest problem happens, not necessarily accuracy of the reduced model, but if your input dimension and output dimension grows a lot, you have 200 inputs, 300 outputs, then this fixed point iteration slows down. Then we got to do something for accelerating that. Is that answering your question? I think Laura, I'm not sure if I should continue.
Maybe conclusion or one more slide?
Okay, another one is, okay, so then maybe I'll skip the theoretical result of this, but one thing that, since I work with ME colleagues a lot, so the second order dynamical systems coming from mass spring damper systems are really important for me. So when you have a mass spring damper system, you want your reduced model to be physically interpretable. You want your system to look like that too, okay? So these systems, for assuming a model damping, you can write them in this way, okay? It is not no longer phi over s minus lambda, but the poles are paired, phi minus s minus lambda plus and lambda minus, okay? You want your reduced model to look like that too. And then again, even to do optimal reduction of the second order dynamical systems, you gotta do Hermite interpolation. You gotta do Hermite interpolation at the mirror images, but now the function you are interpolating becomes multivariate. Then you do mirror images, Hermite interpolation at the mirror images of multivariate function. This thing is everywhere, okay? So if you are doing alpha approximation, you gotta pay attention to mirror images and you have to do Hermite interpolation. We did it for also delay systems. Same thing happens, some parametric systems. And I'm gonna put the conclusions here. Again, this was the main message. Hermite interpolation at the mirror images is the crucial thing for L2 optimal model reduction across different application domains. Stationary problem, dynamic system, parametric problems. And the relational structure is important. One thing is that the way we are approaching these things, Laura, I'm really like, I am just throwing some optimization, just brute force. I would love to find the global means. If I can, there will be huge, huge, huge improvement. And then what we don't know so far, I chose certain measures, but what does this mean if I work with some probabilistic measure? So I want to understand these things moving forward. What does this Hermite interpolation mean? You are matching some variance or there are interesting questions to look in there. And then very recent paper, we showed that we looked at this ERCA algorithm and then we kind of interpreted it as a remaining optimization. And then that opens many more directions. The L2 is still there. So there are many, many interesting problems to look at. And then I'm going to stop here. Thank you very much for paying attention.
Thanks for the beautiful talk. I have two questions. The first one is, how do you choose R dimension?
Very good, very good, very good. So how do I choose R? So for me, the problem I set up is that find the best degree R. So the way I stated, given R, okay? So that is why my starting point. If you don't have any idea, for this, well, let's say for this thing, let's look at this problem. You collect this data, okay? So there is a matrix called Lerner matrix, which is nothing but a divided difference, okay? So you write this matrix, and then there is going back to Anderson and then Antulas 1980s, what they showed is that if this data came from an underlying linear dynamical system, rank of this Lerner matrix is so you can guess these things, okay? So we have other techniques. So this is given R. So we have some other technique where you do greedy search, like you increase the order one by one. Then you stop, but it just doesn't give you this L2 optimality I'm talking about. Is that answering your question?
Yes, Thank you. And my second question, thank you very much. And my second question is, what happens if you drop the condition that the derivative has to be equal between the reduced model and original model? I mean, you impose that the H has to be equal and also H prime has.
Okay, very good, very good. So the question was for those on Zoom, what happens if I drop the Hermite condition? I mean, the first thing is no, you cannot talk about being H2 optimal. It's no longer H2 optimal. Okay,
Yeah.
but what happens is that, so you have R conditions now, but you have two R variables. And then you can use the remaining degrees of freedom to do something else. Maybe you want to preserve structure. Maybe like you infer the fees are positive or something like this. So there are people who are using this. Like you can drop it, but the moment you drop it, you have more degrees of freedom. Then you can minimize. You can try to do something else with those degrees of freedom. So that corresponds to this very early this model reduction. The way I'm doing reduction corresponds to W not equal to V. If you want to do R conditions, you can just choose W is equal to V, and then that will give you R condition. Galerkin projection versus Petrov-Galerkin.
Sure. Thank you. Great.
This is actually related to this part of the presentation. I'm thinking about the case where you don't start from a high dimensional model and reduce down to a low. You start from an infinite dimensional model and reduce down. In that case, it seems to me that there must be some assumption that has to be made about the analyticity of the infinite dimensional model, as well as some maybe hidden assumptions about. I'm assuming that
Beautiful.
the infinite dimensional version has to be in L2, but probably maybe its derivative does as well in order to take those derivatives. So could you speak?
Okay, yes. Question was what happens if I'm going from a infinite dimensional model to reduced model? Indeed, these conditions do not assume H being a finite dimensional rational function. All this requires is that H is enough decay to infinity, and then H minus HR is finite. So we have an example in one of our papers. We start from the PDE for certain boundary conditional observations. We have a transfer function. Like we have an example where our H of S is e to the minus square root of S. And we directly get a rational function for this. And the conditions are the same because this does not require H to be a finite dimensional rational function. It just requires certain analytic assumption, some decay assumption at infinity, but that's it.
You must have to assume something about it being analytic in some domain in order for that to work, right?
Yeah, I am H minus HR has to be analytic. H minus HR, the difference has to be H2.
I see.
Because this thing, like think of it this way, even for the finite dimensional case, if my original transfer function, if I have a feed-through term, think of it this way. If I have a feed-through term, H2 normal of this dynamical system is infinity because of the feed-through term. Okay, but I can, if I choose my HR to have the same feed-through term, then H minus HR will be okay. Again, you need some conditions, absolutely. I'm not claiming that this will apply to every PD. I'm not claiming that at all. But we have cases that you can directly go from, if you can compute the transfer function of the underlying PD, you can go to H2 optimal rational approximate directly, as long as you can evaluate that irrational transfer function. We have beam examples, other stuff. So this, you need to be able to sample H, and you need to be able to sample H prime at the domain. Yes, you have to sample, absolutely, yes, sorry, yes. You have to be able to sample it, yes, absolutely. Is that answering the question?
Yeah.
One question. Yeah, go ahead.
Talk a little bit about the advantages or disadvantages of this compared to like balanced truncation.
Very good. So I don't know how much people are aware of balanced truncation. Balanced truncation is really one of the method of choice in control theory community. Going back to the 1980s, this beautiful method that brings in ideas of reachability, observability. They talk to each other, and then you get a reduced model. So what happens is that when you do balanced truncation, you don't get an H2 optimality, obviously, but you go have an error bound for the H infinity. So that is what I see as the trade-off. Do you want to do H2 or H infinity? I don't want to say balanced truncation is more expensive. In the past, maybe 20 years ago, I would say balanced truncation is more expensive because you are solving Lyapunov equations. But at this day and age, I mean, you can solve large-scale Lyapunov equations. So the cost for this algorithm that we have, ERCA, is that you need to solve sparse linear systems. So from that perspective, this H2 stuff will be slightly cheaper, but I love balanced truncation. So I have nothing against balanced truncation. Yeah.
All right, let's thank our speaker again. If anyone wants to talk more, of course, come on up. Sir Khan will be available. Thank you everyone for coming. We're getting some claps on the Zoom.
I just built it later.
Very nice. Thank you. Thank you. We appreciate it. It is related to the AAA algorithm. Can we implement this?
But it's not like salty and hot or the so I was like walking up and keep writing.
A while ago, I did. Nice meeting you.
Thank you.
It was a great seminar. Yeah.
Thank you. Interpolate does is solve this problem. It linearizes it, so it is more related to discrete altitude. It doesn't grid search. What it does is that
I wasn't here, so not many.
Yes, huh?
Interpolation data gets smaller and deeper. This squares.
Okay, I completely. Yeah, I just looked at this, 45.
Therefore, the parameters, like even multivariate
Everything I have so much, that was a strategy.
Yeah, we were talking about it when I was doing. You do control. You actually don't care if the model is wrong at low frequencies. So in fact, if it's a model that's slightly unstable and slightly stable, if you did time domain simulations, they're going to divert over time and be completely broken. But completely stabilizing one is almost surely going to stabilize another, and there's formal theories of that. So you don't actually care about these long time scale differences.
Yeah.
And you also don't care about differences at very high frequencies, because usually the controllers there's like a middle range where the model has combinations. So when people do like balance translation, they have a weighted model reduction. You're weighting in the combined frequencies.
Okay. Because it reminded me, and actually he mentioned it also in our one-on-one, but it reminded me of sort of like heteroscedastic PCA or whatever, where we have, it's a different thing. It's where there's some data points that we don't expect to fit well because they're from very noisy sensors. But we try to solve these problems also with that weighting, and we also try to understand how to do the weighting. I don't know, I thought it had an interesting similarity.
Increase
The concept is similar, like weighted least-squares and so on. The distinction is your data may be in the time domain, but the right way of weighting this isn't the frequency domain. So the people who do these things, it's very hard to bring these two ideas together. That's a lot of what we were talking about in our one-on-one, is like POD is purely the time domain. So this idea of I'm going to be weighting based on very hard to bring into that. Once you decide to do optimization, a lot of things came up that were like I hear more about deconfiguring. You only alluded to that.
Change it from, it depends on the.
I don't understand.
Yeah, it's not too bad. It's not too bad. Yeah.
You're gonna do the interpolation constraints, but the cost function is also completely different. I'm just.
200, that's gonna take longer to.
Like that's just as so.
Right.
Are you in the Cartesian group
It's
too?
not
or-
a necessary condition, like those particular interpolates.
What are
You
you?
could still like iterate between
Yeah.
points and try to
Yeah.
see.
Okay, I see. Very good. Very good.
Balance package.
Okay, I see. Very good.
Yeah.
Very nice talk.
Thank you so much. Very nice to meet you.
Yeah, I enjoyed it.
Looked at her with your kind
I see. Yeah, but also is a wonderful method. Yeah.
So you you're saying like now there's all the really large scale.
Yes,
Absolutely.
But what order are those? I mean,
There, as long as you have sparsity, 200,000, 300,000, there's, yeah.
and typically they will be sparse or.
They will, I mean, if they my application, they come from discrete series class PDs, we always have sparse.
Okay.
Yes.
Yeah,
But I mean, go up to order 2,000, 3,000, I don't know what type of problems you have. But 2,000, 3,000, 4,000, most computers, you can just do short decomposition and then, yeah.
But what I was interested in is actually not any specific application yet, but asking if we can find the balanced truncation model with maybe like sketching the model.
I see.
Because you, like, in the end, you don't necessarily need the solution if you have a way to get to the low rank approximation of. the
Absolutely.
product.
Totally.
So this is sort of a matrix.
So you can do even better than that probably, because you really even don't need P
Right,
and Q.
that's what I mean, yeah.
You need P and Q acting together. So for the single input, single output case, there is a quantity called cross-gramming. You don't solve two Lyapunov equations, you solve a one Sylvester equation. And then from the single Sylvester equation, indeed, for single output, you can do balance truncation. So that's what we did. We did balance truncation from data. So we collect data. We collect data, and then from this data, indeed, we I can send, if you email, I can send you the paper. Now you don't have to do right now, but send me an email. So we got the balance truncation from data, driven approximation. So, but huh? Yes, no, not at all. Really just input output data. Yeah, just input data. So pretty much what we did. Can you square root implementation of balance truncation?
Yeah.
Okay, so you look at you don't need P and Q, you don't even need U and L. You need this W transpose EV. You write this down, and then what shows up is this two matrices you need. You can just approximate from data directly without even solving Lyapunov equations.
Where is it?
It's in a paper I can send. Yeah. It's in 2024. It's called but I think this idea would be very interesting, I have to say. And then maybe even for the gramming, really, it is AX plus XA plus BC is equal to 0. You solve that, and then I get decomposition of this X cross Gramian, and then that can give you the balance truncation, the single equation.
Okay.
Only for special single output case. Yeah.
Thank you.
No, my pleasure. Thanks for coming. Yeah. Okay.
Okay, so let me finish this one here too.
So